Chapter 8: Unusual and Complex Problems. Our objectives: explain the functions of an attack pumper. Discuss how some appliances can assume the role of an attack pumper. Analyze and solve a variety of types of unusual hydraulic problems. Analyze and solve a variety of types of complex hydraulic problems. Solving complex Siamese problems. Almost every fire officer is aware of the premise that 90% of the fire causes 10% of the fire loss, and 10% of the fire causes 90% of the loss. In fact, in some cities, there are firefighters who have been on the department for 4 or 5 years who have never seen a 2.5-inch line or larger laid at a fire. No doubt there are a number of seasoned pump operators who will someday retire without having once pushed their pumps to their maximum capacity. When looking at the big picture, it is easy to see why some pump operators become complacent in their job. It is the wise pump operator or individual who desires to become a pump operator who thinks about and prepares for unusual situations. The objectives of this chapter is to combine the principles introduced in chapters 5 through 7 to build a foundation for unusual pumping situations. An attack pumper is the water source at a pressure needed to properly supply the nozzle used at a fire. It can be thought of as a large pressurized storage tank equipped with a number of supply outlets. Here's a good example of what your fire truck attack pumper can look like. The solution to adequately supplying each of the lines is to establish a pressure of sufficient magnitude to provide the needs of the lines requiring the most pressure, and then feathering, basically partially closing the outlets to the other lines. Regardless of whether the source is a pumper or a pressurized storage tank, a constant water supply must be maintained in order to supply the requirements for all of the attack lines. This supply to an attack pumper can be provided in several ways. The most common method is to connect the pumper directly to a hydrant through a standard size suction hose. When supplied from a hydrant, either through a short or soft suction or a long, large diameter hose, the hydrant can be considered a supply pumper. On some layouts, for the purpose of solving the hydraulics of a problem, the attack pumper assumes the role of the supply pumper, and appliances such as Ys, water thieves, and manifolds assume the role of the attack pumper. In each of these instances, the lines coming off the appliance can be solved in the same manner as if the lines were coming directly off the outlet of an attack pumper. When several lines are taken off an attack pumper, the general procedure for solving hydraulics problems is to determine the pressure required for each line. The pump operator establishes a discharge pressure to that of the line requiring the highest pressure, and then of course the remaining lines need to be backed down. Remember the formulas for required pump discharge pressure introduced in Chapter 7. Required pump discharge pressure equals nozzle pressure plus friction loss plus any back pressure plus appliance friction loss minus any pressure you gain from height increase. 3 lines have been taken off an attack pumper. Attack line 1 is a single 2.5-inch line that is 300 feet in length, equipped with a fixed gallonage fog nozzle rated at 225 gallons per minute at 100 psi. Attack line 2 is a 2-inch line, 250 feet in length, equipped with a 1-inch smoothbore tip with a nozzle pressure of 50 psi. Attack line 3 is 150 feet of an 1.5-inch line, equipped with a dual gallonage automatic nozzle set to provide 60 gallons per minute. So your pumping scenario looks something like this. So your question, what is the required pump discharge pressure and how should the pump operator handle this situation? So this is actually 3 separate problems. Each of the lines has to be figured separately and then of course pump to the highest line and back down the other 2 lines to the required pressure by partially closing the discharge. So let's go ahead and look at our first line to go ahead and solve. So we have 300 feet of 2.5 flowing 225 gallons per minute with a nozzle pressure of 100 psi. So let's go ahead and do our friction loss for that line. So that's going to be our coefficient, which we got off our chart, which is going to be 2. And then we have 225 gallons. Remember, we're going to divide that by 100. And then our length of hose, which is 300, we're going to divide that by 100. So our friction loss equals 2 times 2.5 square times 3. So when we multiply all that out, we get about 30.375, or we'll call it 0.38 for round numbers. So our friction loss for the first one is 30.38. Now remember, we have to also figure in our nozzle pressure, which is 100. So to get the required flow, it's going to be 100 plus 30.38. So our required PDP is going to be 130.38. So that's our discharge pressure for line 1. Now let's go on to line number 2. Now with line number 2, we have 250 feet of 2-inch, and this is a smooth bore, so that's going to change things up with a 1-inch tip. So that 1-inch tip is going to be 50 psi, so we know we'll have to add that in later. But first we got to figure out the gallons per minute off a 1-inch tip. So that is going to be 29.7 times the diameter square, so that's going to be 1, times the square root of our nozzle pressure, which is going to be 50. I apologize, I cannot write today. So let's go ahead and multiply this out. So 1 times 1 is 1. 1 times 29.7 is 29.7. And then our square root of 50 is going to be about 7.07. So we're going to multiply 29.7 times 7.07, which gives us about 210 gallons per minute. So now we can go ahead and figure our friction loss. So now we go back to our original formula. We get our coefficient off our chart, which is going to be 8. Our gallons per minute, we just figured, is 210. And of course, we divide that by 100, so that's going to be 2.1. And then we're going to, of course, that's times itself. And then we're going to multiply that times our length of hose, which was 250. Again, we're dividing that by 100. So that gives us 2.5. So now we take 8 times 2.1 times 2.1 times 2.5. So let's run it through our calculator here. 2.1 times 2.1. Then we'll multiply that by 8. Then multiply that by 2.5. And that gives us 88.2 for our friction loss. Now we have to add our nozzle pressure. So 88.2 plus, this was a smooth bore, it was a hand line, so our nozzle pressure is going to be 50. We add those together, and we get a required pump discharge pressure of 138.2. Of course, we're just going to pump it at 138. So now we've got 130.38 for our first one and 138 for our second line. Now we got to figure out our third line. Remember, our third line is 150 feet of 1.5 inches, and it's flowing 60 gallons per minute. So let's see here. Our coefficient is going to be 24 for that size line. Our gallons per minute are going to be 60, so we're still dividing that by 100, so that is 0.6. Again, that's square. And then we're going to multiply that by our length of hose, which is 150. Of course, we divide that by 100, which gives us 1.5. Now make sure you don't forget your decimal points, because that'll screw up your answer every time. 0.6 times 0.6 gives you 0.36. And then, of course, multiply that by 24. And then multiply that by our 1.5. And that gives us a discharge pressure of, or excuse me, not discharge pressure, that gives us a friction loss of 12.96, or say 13 for round numbers. And then we know that that is a fog nozzle, that it has to have 100 pounds per square inch on the nozzle. So our required PDP is 113. So our pump can only do pressure, right? And it's pressure in the fire truck, and you have to set it to its highest pressure and then open the valves slowly or close them down a bit to get the lower two pressures. So we know that for line 1, we have to have 130. For line 2, we have to have 138. And for line 3, we're at 113. So we're going to set our highest pump pressure at 138 psi. And then we're just going to close the valve or open the valve just enough to get the other two lines their required pressure. And check our answers, and we are good to go. Okay, the next problem has a supply line run to a Y. Remember, a Y divides the water, and it's assumed that it divides it equally with equal pressure. So we want to add the lines that are taken off the Y. In this problem, the Y assumes the role of the attack pumper. The lines taken off the Y need to be figured separately, then use the highest pressure in the line. So if the flow through the Y is more than 350 gallons per minute, we have to add an additional 10 psi for friction loss. And remember, that's for the appliance. So if you're flowing more than 350 gallons per minute, you have to add 10 psi for whatever appliances you come in contact with. So an attack pumper is supplying a Y through 500 feet of 3.5 inch hose. 3 lines have been taken off the Y for use in attacking the fire. Attack line 1 is a single 2.5 inch line that has 300 feet in length and is equipped with a fixed gallonage fog nozzle rated at 225 gallons per minute at 100 psi. Attack line 2 is a 2-inch line that's 250 feet in length, equipped with a 1-inch smoothbore tip with a nozzle pressure of 50 psi. And attack line 3 is 150 feet of 1.5-inch line, equipped with a dual gallonage automatic nozzle set to provide 60 gallons per minute at 100 psi. Okay, so we already figured out the friction loss for these 3 lines here. So now all we got to do is figure out how much water is coming through here, and if it's over that 350, we're going to have to add that 10 for our appliance, or Y, for friction loss. So we look over here, our flow for the first line was 225. Our flow for the second line, now don't get confused here, because that is a nozzle pressure of 50. And we actually figured out the gallons per minute a minute ago, so that was 210. And then 60 off of this one. So our total gallons being flowed are 495 gallons per minute. So we already know now that we've got to do plus 10 for our appliance. So now we just got to figure out what is our friction loss through 500 feet of 3.5-inch hose. So now we do our friction loss equal our coefficient, which is 0.34. Again, we get that off the chart. Don't forget the decimal. Multiply that by our gallons per minute. So that's 495 divided by 100, which is 4.95. You know, we just have to move the decimal place over twice. And then 500 divided by 100 is 5. So we have 0.34 times 4.95, which is square. So let's do the exponents first. I'm getting bad habits. 4.95 times 4.95. Then we multiply that by 0.34. Then multiply that by 5. And that gives us a friction loss of 41.65. So now we add everything up. So we know that we have to do 41.65 plus 10. So that's 51.65. And then we have to add our original highest gallons per minute, which was 138.2. And then we added all that together, and our required discharge pressure is going to be 189, 0.85, so you might as well say 190 pounds per square inch. And I believe our slide's about 5 pounds off here. I don't think they had it correctly, but yeah, it's 189, or you might as well say 190 pounds per square inch. So let's look at another one. You have two 2.5-inch lines, each 800 feet in length, that have been taken off engine 3 and laid downhill into the standpipe of a 10-story building. The downhill grade is 12%. A single 2.5-inch line, 200 feet in length, has been taken off the standpipe on the 8th floor and is working on a fire on that floor. So the problem looks something like this. You have your pumper, you're pumping downhill at 12% grade. 800 feet of 2.5. So we automatically know we're going to get some head pressure on that. Then you have your standpipe up to the 8th floor, and it's an 1.25 inch tip at 50 psi and 200 feet of 2.5. So again, we'll have to figure out the gallonage on that in just a minute. So what is the required pump discharge pressure for this problem? The standpipe does not assume the role of the attack pumper since there is only one line coming off of the standpipe. So the unusual part about this problem is the fact that you have both forward pressure and back pressure. So you need to figure that into the formula. Remember, both back pressure and forward pressure is just figured out at 0.5 psi per foot of head. So the first thing we do, and I always like doing this first, is starting at the nozzle and working our way back. So we have an 1.25 inch tip, and we have to figure out our gallons per minute. So that's 29.7 times the diameter square times the square root of nozzle pressure. And we figure that out, and you get a discharge of 328 gallons per minute. Now you have to figure the friction loss for the 2.5 inch line and then for the Siamese line. And the total friction loss for those two, again, use your chart and your coefficients, is 86.06. Next, you'll figure out the back pressure. The nozzle is on the 8th floor, so we figure again 7 floors because you don't count the first one, which makes the back pressure 35 psi. Now figure the forward pressure. Remember, the grade is 12% and the distance is 800 feet for a total of 96 feet. So the forward pressure is 0.5 times 96, or again 48. So we have a back pressure of 35, a forward pressure of 48, so we have a difference to the good of about 8 pounds. So you can now solve the required discharge pressure. Our nozzle pressure is 50. Our friction loss off that line is 86.6. Your back pressure is plus 35. Your forward pressure is 48. So you figure that out, and you get 123.6. And now no loss was allowed for the appliance, the Siamese there, because we're flowing less than 350 gallons per minute. And that's going to be your triggering point there. These problems may seem difficult, but if you break them down into small sections, they're really not that complex. You literally just, again, start at the nozzle and work your way back, and then just add all the pieces together at the end. So let's look at another problem. A portable monitor is equipped with 600 gallons per minute fixed gallonage nozzle at 100 psi. It is working on the roof of an 8-story building. There is 500 feet of line of hose that have been taken off engine 6 and laid into the standpipe of the building. 2 of the lines are 3-inch lines with a 2.5 inch coupling, and the other is a 2.5 inch line. 2 3-inch lines with 2.5 inch couplings, each with 200 feet in length, have been taken off the standpipe outlet on the roof and laid into the inlets of the portable monitor. So what is the required pump discharge pressure for engine 6? Now again, when we're figuring these, a couple things to note. Make sure you get the right coefficient, because we have a 3-inch with 2.5 inch coupling, so that's going to change it up just a little bit, but make sure you just pick the right number off the chart. Alright, so since there are 2 lines off the standpipe, you can consider it to be the attack pumper. The pressure at the roof for the standpipe should be figured first, using nozzle pressure plus friction loss plus our appliance friction loss. 25 psi is added for the portable monitor, because that's considered appliance, and we're flowing over that 350 gallons per minute. Friction loss for the hose from the standpipe to the appliance can now be figured. And again, we just use our coefficient and our gallons per minute and our length of hose. So you do the math on that one and you get 14.4 psi. Next, figure the pressure at the standpipe outlet on the roof by working from the nozzle back. So our required pump discharge pressure at the standpipe outlet is as follows. Nozzle pressure plus friction loss plus our appliance. Our nozzle pressure is a given. They gave us that. It's 100 psi. We figured our friction loss is 14.4 psi. And then we add 25 for our appliance because we're over the gallonage. So your required discharge pressure is going to be 139.4. Remember, we are using the standpipe as the attack pumper. Now figure the pressure from the standpipe outlet back to the engine. The pressure requirements at the roof is known, and the appliance friction loss in the standpipe is 10 psi since the flow is greater than 350 gallons per minute. So now our appliance is a standpipe, so we have to add an additional 10 psi on that. It was 25 for the master stream. So using the coefficient for the Siamese line at 600 gallons per minute, with our total gallonage, your friction loss is going to be 21.6. The monitor's on the roof of the 8-story building, so figure 8 floors. So 8 times 0.5, 0.5 per floor gives you friction loss, or not friction loss, pressure loss of 40 psi. So now you can finish the problem. So from the roof outlet to the nozzle was 139. Friction loss was 21.6. Our back pressure was 40. 10 for the appliance. Add it all together, so your required pump discharge pressure is going to be 211 pounds per square inch. So guys, these seem pretty complicated, and I understand that. They can be a head scratcher, but all we're doing is taking what we've learned in the previous chapters and breaking them down into smaller parts. As I said, I recommend starting at the nozzle and working our way back in each section, figuring out your friction loss, your required PDP for each thing. Don't forget your appliances. 10 psi for an appliance with 350, 25 for a master stream, and go all the way down. Figure it out, add it all together, and you'll be good to go. So, you got a lot of math problems this week, so make sure you get cracking on them. Feel free, give me a call in the office if you need any help, or you can email me at aroberts@athenstech.edu. Until next time, be safe and have a great day. And take some Tylenol or Advil prior to doing these math problems, because I'm sure that it'll give you a headache.